Welcome to our lecture on digital basics. So what is digital? Digital is a system that allows us to make easy calculations with circuits. Some systems are digital and some systems are analog. So, what is the difference between digital and analog? Well, if we look at these two graphs, they explain. On the y-axis, we show voltage, and on the x-axis, we show time. In an analog system, the voltage can take on any value, whereas in a digital system, it is limited to either be the low voltage or the high voltage. This is useful because we can use these low and high voltages to do math and all sorts of other operations. So now, I'm sure you're wondering, how do we make these calculations with digital? We use logic gates. What is a logic gate? A logic gate is a way of setting up transistors in a system so that we always get a 1 or a 0 out. This system has multiple different setups, as we can see by all of these different circuit schematics for different gates. We will talk about all of the gates shown here and what their inputs and outputs are. So let's talk about the simplest gate, the NOT gate. The NOT gate does just what it sounds like. It outputs whatever its input is not. So if we get a 0, we output a 1, and if we get a 1, we output a 0. Now, let's talk about a few more advanced logic gates. We have the AND, OR, NOR, and NAND logic gates. An AND logic gate does the logical AND of its two inputs. So we only output a 1 when we have 1 and 1. An OR gate does the logical OR. So it outputs a 1 whenever one of the inputs is a 1. A NOR gate is simply an OR gate that is NOTed. So we take its output and we invert it. So when we have a 0 as an output, now we have a 1. An NAND gate does the exact same thing, but for an AND. The circuit schematics for AND looks like a D, OR has a curve where the AND gate has a straight line, NOR is just an OR gate with a bubble on the front, and an NAND gate is just an AND gate with a bubble on the front. The final gate we will talk about today will be the XOR gate, or exclusive OR, spelled X0R. So, the exclusive OR is very similar to the OR gate, except 1, 1 is 0 as opposed to 1. So, you can only have a 1 as an output if you have one input that is a 1. So, let's do an example that's a little more advanced. We'll try to find the output for a circuit such as this. So, there are a couple ways to go about this. Let's talk about the easiest way. We can look at the truth tables for these individual circuit elements, and then we can combine them and figure out our output. So, remember that the truth table for this one, the AND gate, is 0, 0, 0, 1, 1, 0, 1, 1, and our outputs are 0, 0, 0, 1. So, let's look at our table here. We have a 0 going into a 0 going into B, and a 0 going into C. So B and C, 0, 0, will get 0. A, or our 0, will also get 0. Let's also, for future reference, write out the truth table for the OR gate. Remember that it is 0, 1, 1, 1. So let's try 0, 0, 1. 0 and 1 will get 0. 0 and 0 ORed together will also get 0. Now 0, 1, 0. 1 and 0 will be 0. 0 or 0 will also be 0. Finally, we get to something different. B is 1, C is 1. So we have a 1. A, which is 0, so 0 or 1 is now 1. For this, we can also look and see if we can simplify our gates at all. Let's talk about this OR gate. Anytime we have a 1 at an OR gate, we know that the output of Y will be 1. So, since A is now 1 for the rest of these inputs, we know that our output has to be 1, 1, 1, 1. Let's do one more example. For this example, we will look at this circuit. So, similarly to last time, let's start by writing out each of the circuit elements' logic table. So, for this OR gate, it'll be 0, 0, 0, 1, 1, 0, 1, 1, and our outputs will be 0, 1, 1, 1. For the NOT gate, it'll be 0, 1 will get us 1 or 0. And for the exclusive OR gate, we will have 0, 0, 0, 1, 1, 0, 1, 1 will give us 0, 1, 1, 0. So, let's now look at this circuit. Let's also see if we can apply any of the tricks that will help us to get the answer quicker. So, let's look at this NOT gate. We know that anytime the NOT gate inputs a 0, it will output a 0. A 1, I'm sorry. For this OR gate, we know that anytime the OR gate sees a 1 at its input, it will always output a 1. So, with this knowledge, we can see that anytime C is 0, let me get that on the screen, anytime C is 0, we will have Y as 1. So let's write those in. Now, we also know that anytime we want our XOR gate to output a 1, so that we can go quickly through our OR gate, A and B will have to be 0, 1, or 1, 0. So let's find those on the truth table. 0, 1 is already covered here, but 0, 1 here will now be a 1. Now let's look for 1, 0. This 1, 0 we've already found, but this 1, 0 is now a 1. So, let's check these final two spots. 0, 0, 1. 0, 0 will give us a 0 from the XOR gate. 1 on C will give us a 0 as well, meaning that at the OR gate we will have 0, 0. So 0. Now, let's try 1, 1, 1. Here, we'll have 1, 1 will give us 0, and here at the NOT gate, we'll have 1 will give us 0. So at the OR gate, we'll have two zeros, which will be a 0. Thank you for listening to this lecture on digital logic and logic gates.